When a powertrain code appears, it often points you towards sensors or circuits, but hidden mechanical issues can also trigger these codes. In this lesson, learn how to distinguish mechanical from electrical causes using system logic, scan data, and measurement. Powertrain control relies on a mix of sensor readings and system expectations. Before a fault sets, mechanical issues like a sticking valve or slipping timing can alter sensor inputs just enough to fail plausibility or performance checks. Recognize the context and subtle system responses that hint at a mechanical trigger rather than a direct electrical problem. The ECU evaluates inputs electrically, not physically. It sees voltages, signals, and compares values to its models. Mechanical changes, such as loss of compression or a jammed actuator, alter these inputs in ways that trigger codes, even if the sensor and wiring are healthy. Understanding the module's logic helps you interpret what it can and cannot directly diagnose. Mechanical faults, like a stuck EGR or worn camshaft, change the engine's actual behavior, causing expected sensor signals to deviate. For example, actual air mass or cam position may not match what the ECU commands or expects. Comparing known good values to observed measurements is key to identifying if the electrical circuit is behaving as designed or if underlying mechanics are at fault. To catch hidden faults, many ECUs run plausibility checks, comparing multiple sensors that should agree. For example, manifold pressure and airflow readings, or dual cam sensors. If a mechanical problem disrupts one sensor's values but not another, the ECU may trip a code, even though the circuit itself is fine. Learn to cross-check related PIDs and recognize when data is physically plausible. Direct measurements, such as backprobing a sensor, reading voltage with a multimeter, or using a scope, confirm whether the signal is correct at the sensor and at the ECU. If both show expected voltage, but scan data is off only under certain physical conditions, suspect mechanical root causes, like sticking valves or timing issues. Scan data displays what the ECU interprets, but mechanical issues can cause signals that look valid when tested at rest or out of context, misleading you to suspect a sensor or circuit. Always compare scan tool data to direct measurements and the real system response. Be alert when scan data is plausible, but the engine still behaves abnormally. Don't fall into the trap of replacing sensors or actuators just because a code points their way. Mechanical conditions can set identical DTCs, so always prove the fault with both measurement and system logic before replacing parts. Comparing related PIDs, checking physical behavior, and verifying measurement under symptom conditions prevents costly guesswork. Start with code and freeze frame review. Then compare related sensor data for plausibility. Next, check live measurements at the sensor and ECU under symptom conditions. When values match electrical expectations, probe mechanical causes. This sequence ensures you accurately pinpoint the real failure, mechanical or electrical, without wasted parts or steps. When a powertrain DTC appears, always cross-check sensor data, compare it to direct measurement, and consider mechanical faults if values disagree under load or during operation. This diagnostic discipline saves time, avoids replacing good parts, and reliably identifies the true root cause. Accurate diagnosis means verifying every step. Compare live data to measurement, confirm plausibility, and always rule out mechanical causes before changing parts to solve powertrain codes.